Let's take a look at our final lesson for this chapter. We're going to be utilizing something called a tree diagram to help us determine some probabilities. So first let's take a look at a definition. A tree diagram shows conditional events or probabilities shown in a branch-like display that is helpful in thinking through conditioning. So this branch-like display looks something like this. You'll have some options to start, and then off of those first two options, you'll have some additional options. Perhaps it's 3 additional options. You could have 3 branches to start with and 2 branches off of each one of those. You could have 5 branches to start. It just breaks down what's the possibilities for the first event and what's the possibilities for the second event and putting them together. So let's take a look at several examples that utilize these tree diagrams. So a private college report contains these following statistics. 70% of incoming freshmen attended public school. 75% of public school students who enroll as freshmen eventually graduate. 90% of other freshmen eventually graduate. And we're going to make a tree diagram. So when you look at this, they talk about incoming freshmen, they talk about them attending public school, and then they also talk about them eventually graduating. So when you're making your tree diagram, you have to think about what makes logical sense to come first. They have to enroll in college, or they have to graduate from college. So obviously coming and starting college is the first step. So we know that some of our incoming freshmen attended public schools, but then we have another group. So we don't know, maybe those students were homeschooled, maybe they were private school, we're not sure. So we're simply going to say that our first set of options were either, and there's going to be 2 of them, we're going to say that they either attended public school or they did not attend public school. That will, by saying not attending public school, that puts all of those other options together, like homeschooling, transfer from another university, took some time off, coming back later on in life, or private schools, etc. Now, what we want to look at is what are the percentages that go with each one of these. Well, we know that 70% of incoming freshmen attend public schools. So I'm going to make this 0.7 because we always use decimals. Well, one thing you have to know is all of the branches have to add up to 100. So if 70% attended public school, then 30% did not attend public school. Now, once they've enrolled in college, they go through school, and what happens? They eventually graduate. So these public school students go on to graduate. Well, there is an option instead of graduating. Unfortunately, we do have some students that do not graduate. So that's going to be my other branch. And those same 2 options are going to apply to our non-public people. They either graduate or they do not graduate. Now, let's look at what we know. 75% of public school students who enroll as freshmen eventually graduate. 75% of the public go on to graduate means that 75% is this branch right here. Well, that little pair, graduate and not graduate, has to add up to 100, which means that leaves us 25% here. It also says 90% of other freshmen, those are our not public people, eventually graduate. So not public graduate is 90%, which means, since those have to add up to 100, the remaining is 10%. Now, this is what the tree diagram looks like. We do need to talk about how we use this. So this first pair of branches are the people who go to public school and graduate. Notice I said the word "and" in there. The second pair of branches are those that go to public school and do not graduate. I keep using that word "and" the reason for that is we've learned that "and" means multiply. So I'm going to multiply the options on the branches. So I'm going to take 0.70 times 0.75, and I get 0.525. I'm going to take 0.70 times 0.25, and I'm going to get 0.175. I'm going to take then the not public number, 0.30 times 0.90, and that's going to give me 0.27. And then I'm also going to take 0.30 times 0.10, and I get 0.03. Now, if you want to make sure you're doing this correct, these four numbers that we have here in pink, in red, need to add up to 100. So pick up your calculators, type in 0.525 plus 0.175 plus 0.27 plus 0.03. If you don't get one, you made a mistake. So that's how you make a tree diagram. Now we're going to use that tree diagram to answer 3 additional questions. First question, is there any evidence that a freshman's chances to graduate may depend on what kind of high school the students attended? Well, the 2 graduation numbers are this one and this one. So does it look like where they attended high school might determine where they graduate, what chances they have of graduating? Yes, I'm sorry. The 2 numbers we should have been looking at are the graduation percentages. Those that went to public school only graduated 75% of the time. Those that did not go to public school, all of those other options, graduated 90% of the time. So is there evidence that their chances to graduate depend on what kind of high school? Absolutely. We would say yes, because the graduation rates are different. So when they ask about graduation rates, we look at the 2 different rates and see whether they are the same or different. So now we need to look at 2 more questions. So the first question, what percent of freshmen eventually graduate? This is where we're going to be using the numbers at the very end of the tree diagram. So you need to go to both graduating numbers. Those are the ones that I circled the first time. So we're looking at the people who went to public school and graduated. That was the 0.525. However, there's another option. We also have the people that did not go to public school and graduated, which was 0.27. So the question is, how do I combine those? Well, here's the important word. We have to decide, does it make more sense to put an and there or an or there? So did they come from public school and not public school? Or did they come from public school or not public school? In this case, the word or makes much more sense, and or means add. So 0.525 plus 0.27 equals 0.795. That's the percent of students that eventually graduate. Now let's look at the next question. What percent of students who graduate from college attended a public high school? This is a conditional question because they're not saying what percent of all students. They're saying what percent of students who graduate from college. So we need to start with what percent of students graduated from college. Well, that was the number we just found in the previous part. All students graduating was 0.795. Now we need to look at what part of that total attended a public high school. So we had these 2 numbers up above. Which one of those were our public school graduates? Well, that was this first one. So of the total people who graduated from college, which was 0.795, 0.525 of them were from public school. And so if you type in your calculator 0.525 divided by 0.795, you'll get a decimal. If you hit math, enter, you should get 35 out of 53. So just be careful when you're reading some of those questions, because if they aren't talking about all students, then it's specifically who they're focused on, and it becomes a conditional probability. So that's the end of the first example. Let's look at another example. So, suppose that 23% of adults smoke cigarettes. It is known that 57% of smokers and 13% of non-smokers develop a certain lung condition by age 60. Make a tree diagram. So obviously we're talking about smokers and non-smokers, and we're also talking about lung conditions. So again, think logically, what would make sense to come first? The smoking or non-smoking, or the lung condition? Obviously it makes more sense to be a smoker first. So we're going to start off our tree with 2 branches, because there's only 2 options here. Either they are a smoker or they are a non-smoker. So we see that 23% of adults smoke cigarettes. So there's your smoker percentage, 0.23. Well, if smokers and non-smokers add up to 100, 100 minus 23 is 0.77. So that's the first option. You have 2 options, either you smoke or you don't smoke. So from both of those, then we have 2 more options. It talks about developing a lung condition. So obviously, they're either going to develop a lung condition or they're not going to develop a lung condition. So I'm going to make 2 more sets of branches here. I'm just going to say condition or no condition. And I'm going to do the same thing here. Condition or no condition. So we know from our reading that 57% of smokers developed the condition. So that would be right here. And condition and no condition add up to 100. So 100 minus 57 is 0.43. It also says 13% of non-smokers develop the lung condition. So that's going to go here with non-smokers and condition. And 100 take away 13% is 0.87%. So now we need to finish our tree diagram the same way we finished the public school one. You're doing some multiplying. Smoker and condition, multiply, you'll get 0.1311. Smoker and no condition, multiply, and you'll get 0.9, try that again, 0.0989. Same thing, non-smoker and condition gives you 0.1001. And non-smoker and no condition gives you 0.6699. And if you add up all 4 of those, again, they should add up to 1 if we're doing things correctly. So now we need to explain how these statistics indicate that lung condition and smoking are not independent. So this goes back to a couple of lessons ago. To be independent, the probability of A must equal the probability of A given B. So what we're going to decide, because the given has to come first, so our given has to be the smoker. So we want to decide, does the probability of having the condition equal the probability of having the condition given you're a smoker? So that was, you have to make sure whichever one comes first is your given. So it's going after the bar. The bar is always, what comes after the bar is always the given. So first let's look at simply what's the probability of getting the condition. So the condition numbers are here and here. So this side would be 0.1311 plus 0.1001, which would equal 0.2312. That's the left side taken care of. Now we have to find the probability that they have the condition given they are a smoker. So the numerator is the probability that they have the condition and they are a smoker. The denominator is going to be simply the probability that they are a smoker. So those are the things that we have to find. So what's the probability that they have the condition and they're a smoker? Well, smoker and condition is 0.1311. Out of just a smoker is 0.23. And if we divide 0.133 divided by 0.23, we get 0.57. So for these two things to be independent, my left side and my right side must be equal. Well, I have 0.2312 and 0.57. These are obviously not equal, which also means these are not independent. So make sure when you're looking at independent, it's always the probability of A has to equal the probability of A given B. Let's look at the two extension questions. What's the probability that a randomly selected 60-year-old has this lung condition? So we're choosing from all the 60-year-olds, which is what this entire tree diagram was about. So we just need to look at the two numbers that focus on the lung condition. Well, if you look back at your tree diagram, we had the smoker and lung condition, which was 0.1311. We also had the non-smoker and lung condition, which was 0.1001. And we're going to add those options together, and we get the 0.2312 that we've already used. So now we change the wording. What's the probability that someone with the lung condition was a smoker? So we know up front that they have the lung condition. So this is our given, and then we're trying to find out what's the probability that they were a smoker. So the given, remember, always goes on the bottom. So the lung condition was what we found right here. So the given group of people is 0.2312. Now, out of that amount, which one was the smokers? So we had this total and this total. The first one was the smoker total. The second one was the non-smoker total. So we want the smoker total, which is 0.1311. And so if you take 0.1311, you divide by 0.2312, you get 0.5670. And that's the end of that question. So we're going to look at another one. An airline offers discounted advanced purchase fares to customers who buy tickets more than 30 days before travel and charges regular fares for tickets purchased during those last 30 days. The company has noticed that 60% of its customers take advantage of the advanced purchase fares. The no-show rate, yes, that should say show, among people who paid regular fares is 30%, but only 5% of customers with advanced purchase tickets are no-shows. So first of all, when I say no-show, that means that they bought a ticket, but they didn't actually show up for the flight, which, believe it or not, happens. So again, we ask ourselves, what's going on here? Well, there's two types of tickets. There's advanced purchase and regular. And then obviously, they either show up to the flight or they don't show up. What has to come first? Purchasing the tickets or not showing up? Well, obviously purchasing the tickets comes first. So I either show or I don't show. I'm sorry. Let's try that again. What were my options for tickets? They were either the advanced ones, which were the discounted ones, or the regular ones, which were full price. What percent buy advanced purchases? Well, if we go back, it says the company has noticed that 60% of its customers take advantage of the advanced purchase fares. So I'm going to put a 0.6 here. So if 60% take advantage of the advanced, that means 40% do not. So they've bought their tickets. So now it's time for the flight. They either are going to show or not show. And that's true for both types of tickets. They're either going to show or they're not going to show. So it goes on to say the no-show rate among people who paid regular fare is 30%. So down here we're going to go to regular, show, and I'm going to put a 0.30. Well, I'm sorry, that was the no-show. Move that down. That's down here. So if 30% don't show, the remaining percent is 70. It also says only 5% of customers with advance purchase tickets are no-shows. So this is a tiny 5%, which is not 0.5, it's 0.05, which means 95% show, which is 0.95. So now we need to do our multiplying. Advanced and show is 0.57. Advanced and does not show is 0.03. Regular and show ends up being 0.28 when you multiply, and regular and no show ends up being 0.12. And again, if you add up all four, you should get 100. So let's look at our next part of the questions. What percent of all ticket holders are no-shows? So this is everyone. So go over to your tree diagram and find the no-show bars. The first no-show for the advanced was 0.03. And the no-show for regulars was 0.12. And if we add those together, we get 0.15. Now let's look at the next one. What's the probability that a customer who didn't show had an advance purchase ticket? So now we're not looking at all ticket holders. We're only looking at a customer who didn't show. That is now our given, which means it goes on the bottom. Well, we just answered the no-shows right here. So that's 0.15. We want to know which one of those numbers were our advanced purchase people. Well, the first number, if we go back to our tree, the advanced no-shows were the 0.03. So I'm going to put that right there. 0.03 divided by 0.15, you should get 0.20, or if you use a fraction, 1 out of 5. Last question, is being a no-show independent of the type of ticket? So this is the independent thing. This is the, back to the probability of A has to equal the probability of A given B. Well, remember the given, which is B, has to come first. So that is the type of ticket. Well, it didn't specify. It doesn't matter which one you choose. So you can choose either the advanced or the regular. I'm just going to do the advanced. So the B is the advanced, which means the A is the no-show. So we're trying to find the probability that there was a no-show. And does that equal the probability of a no-show given you bought advanced tickets? So first, the probability of not showing. Well, we found that up in part B. All of our no-shows were 0.15. That's the first part of it. Now let's look at the second part. The probability that they were a no-show given they bought advanced tickets. The given goes on the bottom. So the advanced tickets, if you go back to the actual tree and you look at the first pair of branches, the advanced tickets were 0.60. So then out of the advanced people, okay, the numerator is advanced and they didn't show, which was the 0.03. 0.03 divided by 0.60 comes out to be 0.05. And so are those two numbers equal? They're absolutely not equal, which means these are not independent. All right, we have two examples. These are not more challenging, they just have more to them. So a company manufacturing electronic components for home entertainment systems buys electrical connectors from 3 suppliers. The company prefers to use supplier A because only 1% of those connectors prove to be defective. But supplier A can deliver only 70% of the connectors needed. The company must also purchase connectors from 2 other suppliers, 20% from supplier B and the rest from supplier C. The rates of defective connectors from B and C are 2% and 4% respectively. You buy one of these components, and when you try to use it, you find that the connector is defective. What's the probability that your component came from supplier A? Let's focus on a tree first. You're buying connectors, 3 options, supplier A, B, and C. You get the connectors, and they're either defective, which means they're bad, or they're not defective, which means they are good. So what comes first? You have to buy them first, or they're defective first? Well, you don't know if they're defective until you buy them. So what were our options for buying? There were 3 of them, A, B, and C. So I'm going to start my first problem with 3 sets of branches. Supplier A, supplier B, and supplier C. So what do we know? The company prefers supplier A because only 1% are defective, but supplier A can deliver 70%. So 0.70. We then have the company must also purchase connectors from 2 other suppliers, 20% from B, so 0.20, and the rest from C. Well, 70% plus 20% is 90%. So that means that there's only 10% left. So we've bought our defectors, they've been delivered. We start using them. Well, what's the options? They're either going to work or not work. So they're either going to be good or bad. Instead of writing out the big long words defective and not defective, I'm just going to use good and bad. So A is either going to be good or bad. B is also going to be good or bad. And C is going to be good or bad. So what do we know? Back up to A. They prefer to use A because only 1% of those connectors are defective. So A, only 1% is bad. Now be careful. That's not 0.1, that's 0.01. 99% are good then. So 0.99. Now we got to find B and C. It says the rates of defective components from B and C are 2% and 4% respectively. That means that since B came first, B is 2% bad. So that's not 0.2, it's 0.02, which leaves 98% or 0.98. And C comes second, which is 4%. So bad is 0.04. Good is 96%, which is 0.96. So now pick up your calculators. We got to do a whole bunch of multiplying here. We got 6 numbers to find. Supplier A and good ends up being 0.693. Supplier A and bad ends up being 0.007. If you keep multiplying, supplier B and good comes out to be 0.196. Supplier B and bad comes out to be 0.004. And finally, supplier C and good is 0.096, and supplier C and bad is 0.004. And again, add them all up, they should add up to 1. Now let's actually answer the question. So you buy one of these components, and when you try to use it, you find that the connector is defective or bad. What's the probability that your component came from supplier A? So what do we know first? Because this is a conditional, because they're not talking about all the connectors. We bought a connector. It is defective. That was what we were given to start with. That means defective is on the bottom. And you know what? Let's use the word we've been using for defective is bad. So bad is on the bottom. And then the top, we want to know out of all the bad ones, so they're bad, we want to know which ones came from supplier A. So bad and supplier A. So let's start with the bads. If we look at all of our bad options, we have the first bad option is 0.007. The second bad option is 0.004. And the third bad option is also 0.004. Those are all of the bad ones. Now we need the ones that are bad and from A. So the top one, A, follow the board bad, and we get 0.007. So let's do some combining. We know the top stays 0.007, but if you add up all of the bottoms, you get 0.015. When you divide these, you end up with 0.467, which is our final answer. All right, let's look at our very last example. Okay, so let's look at this last question. A certain company believes 95% of its job applicants are trustworthy. The company gives everyone a polygraph test asking, have you ever stolen anything from your place of work? Naturally, all the applicants answer no, but the polygraph identifies some of those answers as lies, making the person ineligible for a job. Suppose that a polygraph can detect 65% of lies, but incorrectly identifies 15% of true statements as lies. What's the probability that a job applicant rejected under suspicion of dishonesty was actually trustworthy? Very wordy problem. So what's happening? You are being asked if you've ever stolen anything. You're going to say no. Not necessarily the truth, but you're going to say no so that you don't get fired. So the first part of this, have you ever stolen anything? Yes, I've stolen something, or no, I have not stolen something. That's the first pair of our branches. Either you have stolen or you have not stolen. So you either steal from your company or you do not steal. So let's find some numbers that relate to that. Well, nowhere in here does it really talk about stealing or not stealing, but the very first sentence says, a company believes that 95% of its job applicants are trustworthy. So if you're trustworthy, we assume that you do not steal. So that's going to go here, 95%. Well, that means that there's only 5% left, so 0.05. Now that we've decided whether you steal or not steal, you've been asked that question, you said yes or you said no. Now, the question becomes, did you actually tell the truth or did you lie? So that's our next pair of branches. So either you told the truth or you lied. Either you told the truth or you lied. These are not going to be as easy to fill in because you said no, period. We need to see what that means in terms of telling the truth and lying. If you stole something, but you said no, that's a lie. If you stole something and you said yes, that's truth. If you did not steal something and you said no, I did not steal something, this time you're telling the truth. But if you did not steal something and for some stupid reason you said yes, then you lied. Here's the reason that I had to do truth and lie and yeses and nos. Because it says, suppose that a polygraph can detect 65% of lies, but incorrectly identifies 15% of the truth. So they detect 65% of the lies. So if we look at stealing, you lie 65% of the time. Because we have to understand what that means in terms of yeses and nos. Which means you told the truth 35% of the time. So it identified the lie at 65%. I'm sorry. Yeah. Now, here's the tricky part. If you did not steal and you lied, you said yes. But the problem was you didn't say yes. You only said no. So if you did not steal and you said no, you actually told the truth. But the machine incorrectly identifies 15% of the true statements. So we know that 15% of true statements are identified as lies. So if you did not steal, then saying no is telling the truth. But they sometimes misidentified truths as lies. So that means that the 15% is you did not steal, you said no, which was true, but it misidentified that true as a lie. Hopefully that makes sense. And then that means that 100 minus 15, 0.85% of the time, you actually did tell the truth. Let's go through and do all of our multiplying. Stealing and telling the truth is 0.142. No, let me make sure I have the right number. Stealing and telling the truth is 0.0175. Stealing and lying about it is 0.0325. Not stealing and telling the truth is 0.8075. And not stealing and being accused as lying is 0.1425. So let's take a look at the final question. What's the probability that a job applicant rejected under suspicion of dishonesty, which means they lied, was actually trustworthy? So they lied comes first. So that's the denominator. What's the probability of all of the people who lied being trustworthy? Okay, so all the people who lied were the 0.0325 and the 0.1425. Now, the people who lied that were actually trustworthy are the people who do not steal from you. So that do not steal, but still was accused of lying, is 0.1425. So if we take 0.1425, keep that. If we add 0.0325 plus 0.1425, we get 0.175. And I'm running out of space. If you take 0.1425 divided by 0.175, I'm just going to come over here and write it nice and big. We get 0.8143 as our final answer. And that's the end of the lesson.